John Sorce from Stanford. All right, I'll repeat that again since we started recording. Hi, everyone. Today for our UBC virtual seminar, we're very happy to have John Sorce from Stanford, who will be telling us about prospects in large D holography. And reminder that everyone is likely muted in screen sharing or not screen sharing, so John will have a lot of feedback, so you should feel free to interrupt to ask questions and try to make it as interactive as possible for the speaker so it doesn't feel like they're talking to a blank screen, which I know can usually be a problem.
I appreciate that.
Go ahead.
Great. Thank you so much for having me. Thank you, Jason, for inviting me. You know, I was so looking forward to coming to UBC in person, but it's nice to see all of your faces or names on the computer anyway. So the title of this talk is Prospects in Large D Holography, and I'm going to say a word or two about what that means before I start. The first thing to know is that this large D limit, which some of you might not be familiar with, is the limit in which we take a physical theory that we're interested in and we define it in infinitely many space-time dimensions. And especially in general relativity, this limit has proved very useful for doing calculations that aren't analytically tractable in low dimensions. And I'm going to review a little bit of that at the beginning of the talk. But most importantly, I'm going to be talking about how I think we can port this large D mindset over to holography to learn things in our particular field of interest. And I should specify that when I say holography, I'm thinking specifically of it from qubit style holography. You know, there's obviously a lot more to holography than that, and other authors have thought about interesting holographic applications of this large D limit using things like, in fields like holographic hydrodynamics or Yang-Mills theories as models of like quark-gluon plasmas. That's not what I'm going to be talking about. I'm going to be talking about information-theoretic holography and what we can learn in the large D limit. This is based on a particular paper that I wrote late last year with Sean Colin Ellerin and Veronica Hubany, both of whom I think are present, and also Ben Niehoff, who is not present, in which we did a particular large D calculation in holography that I'm going to tell you about. But I think more importantly, our work sets the stage for hopefully future interesting developments in large D holography. And that's what I'm going to try to convince you of, is that this is a thing that you should consider thinking about. So for the outline of the talk, I'm going to start with a little bit of review. Let me tab over to my notes really quickly. I'm going to start with a little bit of review, and I'm going to tell you just a tiny bit in a very non-technical way about large D general relativity. And this is a program in the general relativity literature that was started back in 2013 by Imparan, Suzuki, and Tanabe, and has had many contributors from 2013 to now. And I'm going to tell you a little bit about how this large D program works and what it's good for, but I'm going to focus not so much on the technical results and more on the core intuition, so we can understand why we might be able to port over some of that intuition to our field. After that, I'm going to talk about this particular paper that I mentioned. And what we did in this paper was we identified a particular interesting calculation, which involves the mutual information in the vacuum in ADS-CFT, which becomes analytically tractable in the large D limit. But what I'm going to focus on is what this calculation indicates, which is a phenomenon that I'm going to call entanglement decoupling in large D holography. I'm going to argue for you that what we see in large D holography is a fundamental decoupling of different spatial regions in the boundary theory in an information-theoretic sense. And I'm going to argue for you that that phenomenon is going to make the large D expansion interesting and useful for doing many interesting calculations. The specific calculation that I'm going to talk about, the mutual information calculation I alluded to, I'm going to treat more as a proof of concept than anything else. I'm going to treat it as an indicator that this decoupling is robust and is something that we can use to do other interesting calculations in the future. And with that in mind, I will conclude with a pretty big list of open problems. A big list of problems that I think are particularly suitable for a large D analysis. And in that list of problems, I'm going to emphasize sort of what are the core principles that I think make a problem suitable for a large D analysis? And hopefully we can use those core principles to help understand, when I see a problem, how do I know whether or not large D might be a useful technique to use? The talk I'm going to try to keep fairly short. I'm going to emphasize ideas over technical matter. I'll try to light over a lot of sort of the technical calculations in the paper and focus on giving the intuition behind it. And as such, you should really feel free to interrupt me and ask questions at any time. Like Jason suggested, I'm happy to have this talk be as interactive as possible and fill up as much space as it needs to. So my plan is to start with a little bit of review, unless anyone already has a question about large DGR. So I'm going to tell you the very, very basic idea of what happens in large DGR and why it's useful for studying black holes at large D. And the basic idea is that the Schwarzschild metric, the most basic black hole metric in D+1 dimensions, is controlled almost entirely by this redshift factor, f of r. Some people in the quantum gravity literature call it the emblackening factor, but I came up doing general relativity, so I call it redshift. The Schwarzschild metric is controlled entirely by the profile of this function, f of r. And in D+1 spacetime dimensions, f of r is given by this form, depending on the Schwarzschild radius. It's 1 minus the Schwarzschild radius over r to the power d minus 2. And what's interesting about this function is that in the large D limit, its profile becomes very constrained. It starts, here I'll draw f as a function of r. It starts at 0 at the Schwarzschild radius, and then very, very quickly leaps up to its asymptotic value, which is 1. And the sort of region of radii, the strip that it takes to jump up to that asymptotic value, is of width 1 over d. So what this is telling us is that the actual sort of black hole, part of a black hole metric in large D, becomes very, very thin. And very, very quickly, as you go away from a black hole, you get to this asymptotically flat region. And right now I'm talking about asymptotically flat black holes, but the same principle works in asymptotically ADS or de Sitter. So a way of saying this heuristically is to say that large D black holes have a thin atmosphere. The interesting, oh wait, let me tablet, hold on. There we go. Okay, so they have a thin atmosphere. And what that means is that the interesting profile of the Schwarzschild metric is constrained to be very close to the black hole. Now, why is this useful? Well, suppose I'm a general relativist trying to study some black holes. Let's say I'll put 3 black holes in my spacetime. Well, in large D, what the metric is going to look like is a very, very thin atmosphere around each black hole in which the metric is controlled by the Schwarzschild metric. And then outside, it's going to be asymptotically flat. It's actually not even going to be asymptotically flat. It's just going to be flat. So what this means is that in large D, it's very easy to solve wave equations in a background like this. You can use this simple background to solve wave equations by, say, solving them first in the flat region, then solving them in the near horizon region, then matching the two solutions. And this is what's done in the original large D literature to learn some interesting things about black holes, because in general relativity, a lot of very interesting physical questions can be reduced to the problem of solving wave equations in a particular background. So we can use this, for example, to compute quasi-normal mode spectra of black holes, black brains, objects of that nature. Now, you might object that, well, okay, just because I can compute something in the large D limit doesn't mean I've really learned anything interesting, because, you know, the likelihood is you're probably not that interested in black holes in infinite dimensions. You're probably interested in black holes in about 4 dimensions if you're a general relativist. But what these original authors showed is that you have strong analytical control of these calculations in a 1 over D expansion. And that means that you can do a perturbation series in 1 over d the same way you would do a perturbation series in n in a gauge theory, and you can get good answers in low dimensions, dimensions that you care about. For example, d equals 3, which is for spacetime dimensions, which is what you probably care about if you're a relativist, up to d equals 10, which is 11 spacetime dimensions, which is what you might care about if you're thinking about supergravity. So the point I want to stress about this is, what intuition should we as quantum gravity theorists take from this calculation? And while I framed it as saying that, well, I framed it by saying the large D limit is useful in general relativity because in large D black holes, it is easy to solve wave equations. But that's a very technical way of saying the statement. What I'd like to emphasize is sort of the underlying principle. The reason that wave equations become easy to solve in the large D limit is that we're seeing something that I'd like to call spatial decoupling. And this is the fundamental idea of the large D limit, is that the gravitational field decouples spatially in the large D limit. The gravitational field of a black hole has a near horizon region and a far horizon region, which are effectively decoupled from one another. And it's that decoupling that lets us do this wave equation calculation. So what I'd like to ask is if we can use the same idea in quantum gravity. That we can exploit in quantum gravity to learn something interesting about information-theoretic correlations. So that's the motivation. That's all I want to say about the background. I'll pause for a second if there are any questions, and then I'll go on to talk about the specific paper that I'm talking about today.
Just a quick clarification. By spatial, you mean here specifically radial decoupling, right?
Yes, in this case, I do mean radially. And
okay.
It's actually, that's sort of a good point. Go ahead.
Yeah, I'm just wondering if you meant something more general than just radial decoupling.
No, in this case, I mean radial decoupling. And it's sort of important to note that we have a great amount of symmetry here, which enhances that decoupling, right? The black hole is, in this case, rotationally symmetric. You could also consider some extended black hole, which is, has some internal degrees of freedom, so it's rotationally symmetric in some lower dimension. But we have a rotational symmetry of the black hole, and it's sort of the direction that breaks that symmetry, the radial direction, which experiences this decoupling. And we're going to see a similar kind of thing in holography where we consider very symmetric boundary regions, and we see that they decouple from their exteriors in a similar way.
Yeah, the thing I want to unconfuse myself about is something called local criticality, where different spatial points in the boundary direction decouple from each other. You're not referring to anything like that, right?
Not explicitly, no.
Okay.
Maybe when we get further on, maybe you'll see something like that come up again, and you can interrupt me and tell me your thoughts.
Okay,
but right now, I don't have anything to say about that. Okay, so if there are any other questions? Okay, so we're going to talk about coupling and decoupling phenomena in quantum gravity, and specifically, I mean from the quantum information standpoint. So quantum information-theoretic couplings and decouplings. So when I try to think of coupling and decoupling phenomena, and I haven't been precise about what that means, right? As perhaps the last question got to, I'm just using this very heuristically. But when I think about the idea of coupling and decoupling in quantum information and quantum gravity, the simplest example I can possibly think of something that sounds sort of like that is the mutual information phase transition in the vacuum. So I'm going to go through this example fairly quickly because I assume that many of you have seen it before. But if you haven't, I don't want to assume too much background, so please do feel free to interrupt me and ask questions. So the basic idea, and I'll draw this in ADS3, ADS 2+1, although this does happen in all dimensions, is that if I look at some time slice of the vacuum in ADS CFT, and I look at antipodal boundary regions, A and B, then they have different information-theoretic properties when they're very small versus when they're very large. And that different information-theoretic property comes from the Ryutaki-Nagy formula, where when A and B are small, so the Ryutaki-Nagy formula tells me that to compute the entropy of a region, I should look for the minimal surface anchored to that region. So when A and B are small, that minimal surface is just the union of the two disjoint minimal surfaces that are connected to A and B individually. And when the regions become very large, a different minimal surface becomes smaller, starts to dominate, and we see that entropy is computed by this surface instead. And from the perspective of entanglement wedge reconstruction, these are really very different phases, because in the first phase, the entanglement wedge is this disconnected object that hugs very close to A and B. And in the connected phase, the entanglement wedge is this connected object, which straddles the whole distance between A and B. So in particular, in the left side picture, in this disconnected phase, you can't use A and B to reconstruct operators in the center of the bulk, whereas in the right picture you can. Another way to think about this phase transition is in terms of the mutual information, which you compute via the Ryutake-Inoue formula. So in this disconnected phase, the mutual information between A and B is order 1 in G Newton, order 1 in the holographic expansion. Whereas in the connected phase, if you just follow the RT formula, the mutual information is order 1 over G Newton. So we have a hierarchy of correlation scales in holography, which is controlled by the holographic parameter, G Newton, which we take to 0 in the holographic limit. And what we see is that these two phases are very different in that in the connected phase, these two regions share a very holographically large amount of correlation. An amount of correlation that goes infinite in the holographic limit, whereas in the left-hand side, it's some holographically finite correlation. So the way I would like to say this, in purely sort of intuition-based framing, is that this phase transition is about the spontaneous growth of a connected entanglement wedge. As I scale up these regions, they spontaneously grow a connected entanglement wedge, and in the process, they activate large correlations. And whenever I say large correlations, I mean correlations at order 1 over G Newton. I'm having this hierarchy of correlation scales in mind. And the large correlations are the ones that are at leading order in the holographic parameter. So this is a very basic feature of the Ryutake-Inoue formula, this phase transition that happens in the vacuum. And it's one that I think is familiar to a lot of people. It's very well understood in 3 bulk dimensions, which is d equals 2. But we could ask, since this phenomenon happens in general dimensions, when does this transition happen? What kind of, what size of boundary regions do you need to activate these large correlations? It's a very basic feature of the Ryutake-Inoue formula, so we should certainly understand it. And in d equals 2, which is the case I drew above, it is in fact very well understood. And in fact, it's well understood by symmetry. So in d equals 2, the union of the two intervals, A and B, is topologically equivalent to the complement. The complement, which maybe I'll sort of highlight in red here, is also a union of two intervals. So the phase transition happens exactly when those two intervals become geometrically symmetric, which is when they have the same size. So by symmetry, the transition happens when the volume of AB is exactly half of the volume of the boundary sphere. So another way to say that is that once these two regions, these equal sized regions, collectively take up half of the boundary degrees of freedom, they start activating these large correlations. But something that surprised me when we first started to think about this problem is that in any higher dimension, this calculation is not analytically tractable. You cannot find an analytic answer for where the phase transition happens in higher dimensions. There's a paper by Cartouche collaborators, which looks at d equals 3, which is in the case of 4 bulk dimensions. And they find some closed form expressions for the areas of surfaces in terms of elliptic functions. But even in that case, you can't find a closed form expression for the parameter at which the phase transition happens. So really above d equals 2, this phase transition is not very well understood. So what I'm going to tell you is that we can understand this phase transition in the d equals infinity limit in an analytically tractable way, and we can understand it in a way that gives us insight into lower dimensions and into the general sort of information-theoretic structure of ADS-CFT. So I'm going to frame this as a game, because I think that is sort of it's the way I think about it. Maybe it's not the best way of thinking about it, but it's my talk, so I'm going to give you my intuition. And the way I want to think about this is we're going to play a game in ADS-D+1. And the question is, I guess not how many, but what percentage of the boundary degrees of freedom do I need to activate large correlations? Purely in this antipodal region setup. So the question is basically like, I have two antipodal regions, and I want to activate these large correlations. I want to get this connected entanglement wedge. How much of the boundary do I need to take up before that happens? And knowing sort of how many boundary degrees of freedom I need to activate this, higher class of correlations is going to tell me something about the information theoretic structure of the state. So as it stands, there are only three possible answers to this question. The first one is that it's a vanishingly small fraction. So that would mean that in large dimensions, when I say this question, I mean what is the behavior in the d goes to infinity limit. So suppose it's a vanishingly small fraction. That would mean in terms of the volume of the sphere, I would have very, very small regions at the poles of the sphere that would still have large information theoretic correlations. This one seems unlikely, although you could sort of imagine it happening because the volumes of spheres are very strange in large d, so maybe it's possible. Another option would be the one that is most closely analogous with the understood d equals 2 case, which is an order 1 fraction. So suppose that it's always the case that whenever we get up to half of the boundary degrees of freedom, we activate these large correlations. Maybe it's not exactly half, maybe it's 3/4, maybe it's some transcendental fraction, but there is some definite fraction that once we reach that fraction of boundary degrees of freedom, we get these large correlations. And the only other possibility is that it's 100%. That in the large d limit, you are going to need arbitrarily many of the boundary degrees of freedom in order to activate large correlations. And what I'm going to explain to you is that this turns out to be the right answer. That's something that our calculation shows. Now, before I actually talk about the calculation, let me say a few words about what this means. I'm saying that if I'm in very many space-time dimensions, and I have antipodal regions in the vacuum state, they need to collectively occupy all of the degrees of freedom, or almost all of the degrees of freedom on the boundary, in order to develop large correlations. That indicates to me a very strong notion of decoupling in an information theoretic sense. These antipodal regions decouple quite strongly from one another spatially because I need so many degrees of freedom in order to get any sort of significant correlation between them. I think that on the one hand, this tells us something interesting about the mutual information, right? It's a calculation that we couldn't do in small d that we can do in large d, and that in its own right is interesting. But I think also, and this is sort of the proof of concept thing I alluded to at the start of this talk, this is going to give us, this indicates to us that we have a spatial decoupling phenomenon in terms of information theoretic correlations in large D holography. And that suggests to me, the fact that we have some kind of decoupling phenomenon suggests to me that large D will be useful for doing other calculations as well. And that's going to be what I talk about at the end of this talk when I give my list of problems. But that's really what I wanted to emphasize. So I'm going to talk next a little bit about the technique that we use in the paper, but I'd like to pause and see if there are any questions about what I said so far.
Can I ask you a question?
Yeah, absolutely, Matt.
Just to clarify, maybe you said this and I missed it, but you're talking about spherical caps on a sphere?
Yes, I'm talking about spherical caps on a time slice of ADS-D plus 1.
So A and B are each, is it, okay, A and B, each of A and B is a spherical cap that
It's
are
a spherical cap,
each
yeah.
other.
Yeah,
Of the
and they're
same
equal size. Yeah, they're the same size.
Okay, thanks.
Yeah, and I'll draw a picture of that in a moment when I talk about the details. But yeah, that is the game. So part of the reason we were inspired to do this was because we were trying to see, like, what is the most, we were trying to figure out what is the sort of biggest number of degrees of freedom you could get on the boundary without activating these large correlations. And our guess was that the antipodal caps would be the sort of the optimal ones for that. Would be right if I had antipodal caps, that's sort of the, I could imagine that that's the biggest I could get to regions while still being in the disconnected phase.
Can I ask a question?
Yes.
Yeah, so it's probably going to come up later, but is it clear that there's a unique, meaningful large D limit of this question? I could imagine scaling. I mean, I could imagine scaling different quantities differently from D. You can presumably get different answers here.
So because the question we're asking, because we've reduced it to a purely geometric question, there is a unique large D notion of that, because we're just talking about large D hyperbolic geometry, and the hyperbolic metric is well defined in large D. Right? I mean, in any dimension, there's a sort of a unique hyperbolic metric and a preferred spherical metric on the boundary. And we're asking all of our questions with respect to those two metrics, right? We're asking a question about hyperbolic geometry, and this notion of the percentage of boundary degrees of freedom is asked with respect to the unique spherical metric that I put on the boundary.
Okay.
You could ask things like, well, if I want this to be a quantum gravity question, then things happen in large D that are different than low dimensions. There's a huge number of species of particles in string theory in large D that could add quantum effects that we're not taking into account. But because we've taken the geometric problem, this geometric problem is well defined in large D. In terms of quantum gravity, you could say that we are taking the G Newton goes to 0 limit before we take the D goes to infinity limit. And that makes the problem geometrically well defined.
Sure.
Yeah. Do you have a further question? Okay, I don't hear anything.
A question, John.
Yes.
So you mentioned that you are taking Gn goes to 0 first, but do you think your result would still apply if you don't take that limit point?
Well, I really haven't thought about this very carefully, because if you don't take G Newton goes to 0 first, then you end up with quantum effects, which are enhanced in large dimensions. There are these calculations that show, for example, that black holes evaporate very, very quickly in large dimensions because there's a huge number of species of particles. I admit I'm really not an expert on this. Since we're working in the vacuum, I sort of suspect that everything I'm saying now is not really dependent on quantum effects, but for my own sanity, I'm going to really just treat this as a geometric problem and not worry too much about the details of that.
Thanks.
Yeah, unless somehow gravitational fluctuations become very, very important in large dimensions, which is possible. I don't know very much about these things. Okay, so I'm going to tell you a little bit about the actual technique of the paper. And like with the rest of this talk, I'm really not going to talk about the technical details of the calculation. There are going to be some integrals that I won't write down because I don't think that looking at the integrands will really help you understand it. I'm going to try to emphasize the techniques and why they work, and you can look at the paper for details. So the basic idea, the geometric problem that we're trying to solve, and I'll draw a picture, the one that Matt was suggesting earlier. We're asking a geometric question about minimal surfaces in d-dimensional hyperbolic space. So I'll draw, for example, H3, which is topologically the interior of a two-sphere. And I'm considering two polar caps of equal size, one at the North Pole, which I'll call A, and one at the South Pole, which I'll call B. Okay, so there are two candidates for what the minimal surface of A union B could be. Either we could have two spherical cap-like surfaces that hug very closely to A and B separately, or we could have a single connected tube-like surface that goes between the two. These are both minimal surfaces, and they both exist. I should add a caveat, which is kind of interesting, which is that this tube-like surface only exists when A and B are sufficiently large. If A and B are very small regions, then there's no tube-like surface, and the only minimal surfaces are these small cap-like ones. But when A and B become large, which is the regime where the phase transition happens, this surface starts to exist, and then we need to start comparing the size of the surfaces. So fundamentally, the question we're going to be asking is a geometric question, which is when does the surface area of this tube equal the surface area of the two caps? Because that's going to be where the phase transition happens. That's when the tube-like surface becomes of equal area to the cap-like surfaces. And after that point, the tube-like, if I keep making the regions bigger, the tube-like surface will become smaller and will start to dominate. Will become the crucial sort of Ryuta-Kinagi surface for the system. Now, in order to solve this problem, it helps to know a few facts about hyperbolic geometry. And the first and most important fact is that these cap-like surfaces foliate hyperbolic space. That on its own is probably fairly obvious. Let me draw this in H2. is that if I take H2 and I draw all of the cap-like surfaces that are centered at either the north or the south pole, then they look like this. They form some complete foliation of the spacetime. But because this is a foliation by minimal surfaces, it also turns out that the normal vectors to these surfaces are killing vectors. In other words, they generate an isometry of the spacetime. I don't actually think this should be too surprising. All I'm really telling you is that there's an isometry of hyperbolic space that takes any of these red lines to any of the other red lines. This should actually probably be, it might not be immediately obvious if you haven't thought about this before, but I'm going to claim to you that it should be obvious. And the reason for that is that you probably know that isometries in hyperbolic space are just conformal transformations on the boundary. And if I consider the conformal transformation on the boundary that is a dilatation centered at the North Pole, all that's going to do is push everything on the sphere down and around the sphere from the North Pole to the South Pole. And what that's going to do, I'm just blowing up the North Pole and pushing everything down towards the South Pole. And all that does is it pushes these red surfaces down into each other. So there's some family of isometries that relates to these spherical caps. And that gives us two things. For one thing, it means that if we use a coordinate system that's adapted to these surfaces, it's going to be very simple. Let me explain that before I tell you the second thing it gives us. So I'm going to use coordinates that are adapted to these cap-like surfaces. And I'll draw this again in H2. So the first thing I'm going to do is I'm going to make one of my coordinates tell me which of these cap-like surfaces I'm on. And the convention that we've used in the paper is that that coordinate is called eta. And we have eta equals infinity at the North Pole, eta equals 0 at the equator, and eta equals minus infinity at the South Pole. I need one more coordinate, which I'm going to do by taking all of the surfaces that are orthogonal to these cap-like surfaces, and having another coordinate that tells me which of those surfaces I'm on. So if I specify eta, which tells me which red surface I'm on, and I specify a different coordinate, which tells me which blue surface I'm on, I've uniquely specified a point in the spacetime up to the internal spherical symmetry, which has its own coordinates. So the coordinate I'm going to use, I'm going to call zeta. And the convention we've chosen for zeta in our paper is that zeta is the angle that the blue surface makes with the axis of the sphere. So for example, this central line is the axis of the sphere, so the angle it makes with the axis is zeta equals 0. The boundary is another surface of constant zeta, and it makes angle pi over 2 with the axis, right? It meets the axis at the North Pole, and it makes angle pi over 2 there. So we just have a different system of coordinates, which tells us which of these blue surfaces we're on. And you can use these coordinates in arbitrary dimensions. Perhaps I'll just write down the metric for your edification, although it's not particularly important for this talk. It's a lot like a standard, it is the hyperbolic metric in a different system of coordinates. It's a lot like a standard hyperbolic metric, where out front I have this factor that blows up when we go to the boundary, which is zeta equals pi over 2. And then I have this simple metric, which doesn't depend on the parameter eta because that's an isometry. It's a killing parameter. Okay, so one of the things that this coordinate system gives us is that it is very simple. We've used the fact that we have an isometry to drop one of our coordinates out of the metric. That's going to make all of our calculations simple. But another thing it gives us is that I said before, this is sort of conceptual, so I'm going to try to make this clear. Every single one of these caps is related to one another by an isometry, right? And so when we try to solve the equation, twice the area of the cap equals the area of the tube, which is what we're trying to solve to find the phase transition, the area of the cap is going to be universal because every cap is related to another cap by an isometry. Now, this didn't necessarily have to be true because even though the quantities like the mutual information are regulator independent, the areas of surfaces can be regulator dependent. And so depending on what regulator I choose, the area of two different caps, even though they're related to by isometries, might be different if the regulator doesn't play nicely with the isometries. But because we've chosen our coordinates to be adapted to the isometries that map us between these caps, any regulator associated with those coordinates is going to preserve that isometry property. So it's going to make the area of the caps universal. And that is what sort of really crucially, that is one thing that really crucially simplifies this calculation. It means that all we really have to do in this system of coordinates is we have some universal number that gives the area of a cap in these coordinates with respect to whatever regulator we use in these coordinates. And all we're trying to do is find which tube has area given by that universal number. I'll pause for questions because I know that's maybe a little conceptual. If anyone has a question, I'm happy to answer it. I'll draw a picture while I wait. Okay, given no questions, I'll say that what we're trying to do is look at tube-like surfaces, tube-like minimal surfaces, and figure out which one solves the equation a tube equals twice the area of the cap, where the area of the cap is something universal. And in order to solve this question, in order to solve this equation, we need some way of parametrizing the different tube-like minimal surfaces. And the way we choose to do that in our paper is to parameterize them by the minimal value of zeta that they reach. Right? The tubes sort of come in from the boundary and reach some turning point and then go back out to the boundary. And that turning point is at some unique value of this coordinate zeta, which says which of these blue surfaces is the last one that the tube meets before going back out. And we call that number zeta star. And you can show quite easily that there is a unique tube associated to each, a unique minimal tube associated to each value of zeta star. So what we're really trying to do is solve the equation area of the tube as a function of zeta star equals twice the area of the cap. And this thing is some integral equation. It's an integral equation for zeta star. It's this geometric integral over these different minimal surfaces. You need to use the equations of motion for the minimal surface. But if you just write this down, we go through the technical details in the paper, but I suspect if you write down this equation and these coordinates, then you'll see quite readily that you can solve perturbatively in the d goes to infinity limit. And that is really all I'm going to say about the technical matter of this calculation. Like I said, I'm not going to write down the integrands. I'm not going to write down the integrals. There are some tricks you need to do with changes of variables to make it tractable and to actually solve it analytically, but you can look at the paper if you want to know that. Crucially, what we can do is that we can solve for zeta star in a power series in d-2. And you can do that analytically, at least for the first few powers. So
John,
I will, yes, absolutely, Matt.
Do you have the solution analytically for the tube at finite d, or are you solving that differential equation also only in the d goes to infinity limit?
So you don't, it's only in the d goes to infinity limit because you don't actually solve for the tube. What you do is you write down the integral for the area, and then you plug in the differential equation for the tube, which simplifies the integral, because you're assuming that you're integrating over something that solves those equations of motion, but you never actually find the surface that solves the equations of motion. You just find its area. Because the point is that given a particular critical value of zeta, there is only one tube that solves the equations of motion. So you can solve for its area by integrating even without knowing exactly what the surface is.
I see, okay.
Yeah, and that's one of the crucial things that makes this calculation possible. I suspect we actually could find a d goes to infinity expression for the tube, although I haven't thought about this in a while, so I'm afraid I don't have anything more to say about that on the top of my head. But let me tell you what the answer is. And I'm going to tell you what the answer is. I'll call this theta star critical to emphasize that this is the value of zeta star that saturates this equation. And you can go through all the rigmarole of translating this to a boundary position and going back into spherical coordinates, which are the ones we understand quite well. And you get a critical angle at which the spherical caps develop connected entanglement wedge. And just to be clear with what I mean by that critical angle, I mean, here are the caps on the sphere, and the critical angle is this angle here, theta c. The angle at which, as soon as you have an angle bigger than theta c, you're going to have a connected entanglement wedge. And the answer is this. It's pi over 2. Well, that makes sense. The leading order behavior is pi over 2 because in the limit as d goes to infinity, these things are going to become larger and larger, and they'll limit to the equator. But what's really interesting is what the first correction to this is. The first correction happens at 1 over d minus 2 times pi over 4. That coefficient isn't particularly important. And then there's terms at order 1 over d minus 2 squared. Okay, so I claim that this scaling, this 1 over d minus 2 scaling, is very, very interesting. It was the thing that surprised me most when we started this project. And I'll tell you a fact, which I won't verify, which is that if these caps were to take up a finite fraction of the area of the boundary sphere, that scaling would be different. An order 1 fraction, any order 1 fraction of the boundary volume would go like pi over 2 minus order 1 over square root d minus 2. A 1 over square root d scaling is what gives you a finite fraction of the area. I'll give you a very heuristic way to see that, which is that, I'll just say these words, and if they don't immediately register to you, that's okay. It's not super important for the talk. You can go look at the paper. But the idea is that the volume element, or the area element, on a d-dimensional sphere goes like sine to the d, or cosine to the d, depending on your choice of coordinates, which in the limit as d goes to infinity looks like a d-dependent Gaussian. It looks like e to the minus d theta squared, or something like that. And so this square root d comes from the error estimates on the Gaussian, basically. This 1 over square root d comes from having some finite fraction of a Gaussian distribution with that width. We explain this in a footnote in the paper, and I encourage you to go look at that if you want more details. But what we're seeing is that the critical angle at which the phase transition actually happens limits to the equator faster than any finite fraction of the boundary area. So this is the claim I initially made, that these regions need to collectively occupy, in the limit d goes to infinity, 100% of the boundary degrees of freedom by volume. And that indicates to me a very, very, very strong notion of decoupling. One other thing I'll tell you, which I think is sort of just useful to keep in mind going forward, is that we can keep going. We can go to higher orders in this perturbation series. We only went to 1 higher order because the integral became nasty after that, and we didn't want to do it. But if you go to 1 higher order, you get pretty good answers down to 6 bulk dimensions. So that's d equals 5. If you add 1 order, and we found the actual critical parameter numerically in low dimensions, and then we compared it to the answer that we got from this perturbation series. So if I add 1 term to this perturbation series, I get the 6-dimensional answer to within 4%. I get the 4-dimensional answer, I think, to within 30%, but it's no surprising that you can't get a good 4-dimensional answer because 4 dimensions is d equals 3, and our perturbation series is 1 over d minus 2, so d equals 3 is not constrained by the perturbation series. But you can still get good answers down to d equals 5, which is still, as far as I'm concerned, a perfectly interesting space-time dimension to care about. Okay, so I hope I've convinced you both that we have this interesting decoupling phenomenon, and also that we can get good answers in a perturbation series, which indicates to me that this technique has legs. It's something we should take quite seriously as something that our community can use. That is all I want to say about the geometric aspects of this paper. I'm going to talk a little bit about some quantum information intuition, and then I'm going to talk about the list of problems that I wanted to share. But if anyone has any questions about the geometric stuff here, now would be a great time to ask them.
I have a question. This is again. Should I go ahead, or did somebody else have a question?
Why don't you go, Matt?
Well, this is related to my previous question, so I don't know if you know the answer off the top of your head, but what does the tube look like in this? What does the tube look like at large D?
Yeah, I can show you.
Limit to kind of meeting up with the spherical cap? I mean, the
yes,
minimal surface?
it does. We have plots of them in the paper. You know what, actually? Maybe I could pull up a figure from the paper rather than trying to draw it. Let me see if I have, yeah, let me pull that up. You're all going to see my terrible LaTeX patterns. Here we go. Okay. So the cross sections of the tubes look like this. So in they basically become very, very narrow. What you're seeing in this figure is the red line, which is the sort of widest tube that you're, or I guess the biggest tube, the one that is, this tube is the one in D equals 2. That's the one that everyone knows, the three-dimensional bulk case, where they take up the boundary volume of, they take up half the boundary volume. And then what you see is that very quickly, as you go up in dimensions, they tend to narrow out. And they limit to some very, very narrow tube, which you're seeing in sort of this blue line here.
But they don't reach the center.
No, they don't reach the center. They have some limiting, there is some critical value that they limit to, which is, if I remember correctly, it's zeta critical equals pi over 4. I can look in the paper, or if Veronica or Sean are here, they can tell me whether that's correct, but I think it's pi over 4.
I think that's correct.
Thank you, Veronica. Yeah, we have a nice, here, yeah, it limits to pi over 4 in our nice little table. So they don't limit to the center. Yeah, the tube-like surfaces limit to taking up some, you know, everything inside this little sort of blocked out strip here. That said, I mean, I'm not actually sure whether that's an artifact of the coordinate system. I tend to think it's not. You know, there is some like finite distance between, there's some finite sort of neck of this tube that I'm not sure we ever computed what the width of that neck was in large dimensions. That's probably an interesting thing to know that I don't know off the top of my head, but it's easy to compute.
But it must have a vanishing area compared to the annulus or whatever, the part that it does cover.
A vanishing area? What do you mean? What would have a vanishing area?
That red line, the disk that it doesn't cover,
yeah,
the annulus that it does cover.
Yes. Yeah.
I mean,
Why do
since
you
you're in
say
infinite dimensions, it can have a finite radius, but a vanishing area in the limit as d goes to infinity.
So I do want to be clear, Matt, that the regions A and B are like here.
No, I understand.
So, okay, so the disk is inside the entanglement wedge.
I understand that. It's the neck, it's the entanglement wedge cross section.
Yeah, exactly. Why are you saying that the area of the entanglement wedge cross section must vanish?
Because you're comparing it, because the other candidate minimal surface is two hemispheres, I guess, or disks.
Yeah, spherical caps.
Yeah, well, that actually kind of cover that entanglement wedge cross section.
Yeah, but so the area of the tube.
There's 2 of them, Matt. So
yeah.
I know, but you've covered, well, anyway, all right. I could explain, I mean, yeah, if
I
you
sort of see,
draw
you're
the
saying that
hemispherical cross section,
the area of the
into
cap,
an annulus and a center, and the center
I see what you're saying.
must have vanishing area compared to the annulus.
You're saying that the area of the cap
the
must be.
Of 2.
Yeah, you're suggesting that this equation is basically what you're saying, right? The area of the cap is like some annulus plus a disk, and the tube is like twice the annulus.
Yeah.
Plus something, which
and
could
you're
be
comparing twice the cap to the tube.
Yes, but the disk doesn't necessarily. twice the cap is bigger than the tube, though, right?
Well,
Is
they're
sort of
the
the
same
point.
at the critical point, right?
Yes. Yeah, at the critical point, they're the same. Okay, I see what you're saying. That seems reasonable. Yeah, in order for these two things to match, then you would need the disk to be vanishingly small. I think I can buy that. Although, you know, since these two surfaces don't perfectly match, maybe the minor fluctuations between the two could make up for that. But I think that's a reasonable guess.
John, I think there's also another effect, which is that the turnaround points have the largest area contribution in high D.
Yes, they do.
And, so
and that's what I put in this little squiggle here. This squiggle is the other part of the tube, and that actually has a huge amount of area because of measure concentration around the equator of the sphere at large D. So there's actually a huge amount of area in these little bits here. So Ted Jacobson, I think, said in the chat, at the critical point, it's not an annulus. Ted, what we mean by this is that you can sort of think of the tube as being two annuluses stacked on top of each other, together with some connecting strip. And the debate is sort of the relative size of those annuluses with pieces of these spherical caps. But Veronica is pointing out that there is some contribution from this strip, but Veronica, that actually goes in favor of mass point, because that would add some extra stuff to the tube, which would suggest that the disk really would need to be quite small at the critical point.
So the two cap, the parts of the blue surface's contribution to the cap would be missing. The cap things have the extra area in the middle that would have been mass contribution, but you're comparing that contribution to the turnaround points, right?
Yeah. Yeah, the equation we're seeing is basically twice the annulus plus twice the disk is equal to twice the annulus
plus turnaround.
Oh, I see what you're saying. Yeah, actually, plus turnaround.
Yeah, so the turnarounds could be large, so the disk areas could be large.
Okay, thank you for that point, Veronica. Yeah, so Matt, I am inclined to agree with that here, that because there is a huge amount of area concentrated in these turnaround points, that would have to be made up for in the disk. So I'm actually thinking that the disk will have significant area.
But I mean, I think we just know from that at high D, yeah, I think just from the measure, since you're at high D, the disk must have vanishing area compared to the annulus, if it has a finite relative radius.
Yeah, that's, yeah. You know what, I think after we get off this call, I'll do the calculation and we'll find out if it's anything interesting. Ted also pointed out in the chat that the two different annular surfaces don't coincide, and perhaps the differences between them are significant. This is a very heuristic discussion. I think it's a good point, Matt. I don't know off the top of my head what the right answer is.
Okay, thanks.
Yeah. Anything else on this before I go on? I think it was a great discussion. Thank you for bringing it up. I just don't have a definite answer.
I said a question about the phase transition. So
yeah,
you might have guessed that that's what would happen just from looking at conformal correlators in large dimensions that shows that they decouple at separated points. Were you guys able to cook up any more general CFT arguments, not using holography, that the transition should occur?
So we were not. It's one of my list of problems at the end. And maybe when I get there, so Sean Colin-Ellery, who's one of the authors on the paper, spent a fair amount of time thinking about this. So if he's still here at the end when I get to that part, maybe I'll invite him to say a few words about it, and that will hopefully answer your question. Okay, cool. So let me say a few words about the quantum information intuition. And everything I'm about to tell you is really well known to quantum information theorists, but perhaps not as well known to those of us in the quantum gravity community. And this is about decoupling and monogamy of entanglement at large D. So really, I'm gonna only say a few lines about this, but I wanna give you some intuition for why this kind of decoupling happens. And we have a whole section in the paper about this if you want sort of more detail on these arguments. But the idea is that imagine I have some quantum system on a lattice. I'll draw a cubic lattice for simplicity, but it really could be any regular lattice. And we'll look at the vertex V in the center. And the idea is to notice that the number of neighbors of any given vertex scales with the dimension of the lattice. Now let's imagine I put some quantum system on this lattice. And let's furthermore suppose that I'm in an isotropic state. So perhaps I'm in the ground state, like the unique ground state of an isotropic Hamiltonian. And what that means is that this vertex can't distinguish between its neighbors. All of its neighbors are the same, and in particular, that means it has to be entangled with each of its neighbors equally. So let's look at the entanglement between V and one of its neighbors. And I'm being very heuristic here. I'm not writing any sort of explicit formula. What you might imagine is that because V is equally entangled with all of its neighbors, and because the principle of monogamy of entanglement tells us that a single quantum system can't be hugely entangled with a large number of quantum systems, you might imagine that the entanglement with any one neighbor has to scale like 1 over the number of neighbors, which in the large D limit goes like 1 over D. There are ways to make this precise. We do this in the paper. They use things called quantum Definity theorems. I should emphasize that the results that we put in the paper about these are new only to high energy theorists. They're not new to quantum information theorists who have known this kind of thing for a while. But it really is true that in a precise sense, using certain entanglement measures that are very precise, the entanglement between any two neighboring sites in the ground state of an isotropic lattice system becomes vanishingly small on the limit of a large number of dimensions. And I think that's sort of what we're seeing happen here, is that because in a large number of dimensions, every single site has a large number of neighbors, it's not too correlated with any one of them individually. And if we look at this kind of decoupling that I drew earlier, if we look at these spherical caps, we can sort of imagine that in a large number of dimensions, there's only one direction that goes between the two caps, and a huge number of directions, in fact, d minus 2 directions, that go tangentially to the caps. So what we're seeing is that the entanglement between the caps, the entanglement along this sort of one transverse direction, is heavily suppressed by the large D. The caps can't be very strongly entangled with each other because they're very highly entangled with themselves, is basically what's happening here. That's purely intuition. There's some precise statements in the paper. I will say that while this argument can give you quite precisely that the entanglement should be suppressed at large D, it doesn't tell you that classical correlation should be suppressed at large D. And because we're finding that the mutual information is suppressed at large D, we are also finding that classical correlations decouple. Perhaps you could take this as further evidence towards this conjecture that quantum correlations dominate over classical ones in ADS-CFT. That's speculative, but I think it's something worth thinking about. Okay, now let's talk about outlook.
A small question.
Yes, of course.
So you briefly mentioned that this holds for the ground state, but it seems like it should work for excited states as well.
So the quantum information argument that I made?
Yeah.
The quantum information argument works for any isotropic state. Mm-hmm. So it works for any state that is equally entangled with all of its neighbors.
Oh, okay, I see. Mm-hmm.
Yeah. So if you have an isotropic Hamiltonian and you have any non-degenerate energy state, then that'll be the case, for example.
I see. Okay, yeah, thank you.
Yeah. Okay, good. So I'm going to give you a list of problems that I think one should try to do in large D that I have not tried to do. So perhaps for some of you who are eager to find something new to do, these will be good ideas. I want to first advertise 2 pieces of work that I know are currently being done by authors who I respect and therefore want to plug. Roberto Amparo and collaborators are working currently on studying the holographic renormalization group in large D. I unfortunately don't actually know much about what's going on in this work, but they seem to have some very interesting results. Roberto, actually, are you here? Are you interested in saying a sentence or two about that for the benefit of everyone here?
Yeah, hello. Yeah, I can say a few things. Yeah, we have results on the Pfeffer-Gram expansion, where you reconstruct the bulk starting from boundary data. And that's something that we find that it simplifies a lot, this expansion, the Febvre-Mangram expansion. In principle, as you go to higher and higher dimensions, you have more and more terms that you have to take into account. What we find is that when you take the large D limit, everything simplifies and you just have to keep one term. So bulk reconstruction in the sense of Febvre-Mangram, that seems to simplify a lot.
Great. Okay. That sounds very interesting. Thank you, Roberto. Cool. So that's an advertisement. You should all keep an eye out for that when Roberto and his collaborators finish. Another interesting thing that I know is currently being done is by Shamit Kotrou and Milind Shayani. I wrote the first name instead of the last name. Shamit and Milind, who are working on what is called dynamical mean field theory. The basic idea of this, as I understand it, is that I told you above that there's a spatial decoupling of degrees of freedom at large D in most quantum mechanical systems, which is sometimes called the mean field theory limit, because it is sort of equivalent to assuming that every spatial site is decoupled from one another. And it happens to be true that there is this spatial decoupling in the limit of large D lattice systems. What they're studying is something called dynamical mean field theory, where there are certain interesting quantities that seem to have a sort of temporal decoupling, in the same sense that this lattice entanglement has a spatial decoupling. And they're trying to understand that using large D holography. I'm afraid I don't know any more details, but I thought I should advertise it because it sounds like interesting work. There are many other interesting developments in this field. I would like to plug a really good recent review by Roberto and Chris Herzog, just from, I think, even last month. And I'll write the archive number here, where they go over in detail a lot of the interesting developments that have been made in the large D GR program, and they make some comments at the end about holographic directions. But now I'll give you my own list of problems. And the perspective I want to stress is that all of these are going to be problems that in some sense involve coupling or decoupling phenomena, information theoretically. And I suspect that anything that we can think of at its core as being a problem of coupling or decoupling will be tractable in a large D analysis, as long as we ask the right question. So as a first problem, and one that I think someone should really spend some time on, is the problem of shape deformations of extremal surfaces. This is a geometric problem, but it's one that is very closely related to a lot of interesting holographic physics. And I'll say those relations in a second, but first let me just say the basics of what the geometric problem is. Imagine I have some holographic boundary, and I have some region on the boundary, and off of that region into the bulk, there is some extremal surface, right? Here's my extremal surface. Now the idea is that if I make some deformation of the boundary region, that's going to propagate up and become some deformation of the extremal surface. And perturbatively, you can study that deformation as some field on the background extremal surface, right? You can say, well, you can treat this as basically a metric perturbation to the background extremal surface for a small enough deformation, and you can study it in terms of the geometry of the background surface. Now, what I suspect is that for a sufficiently symmetric boundary region, you're going to have a sufficiently symmetric extremal surface, and that thing is going to have a large number of internal dimensions, which I suspect in some precise sense, although I haven't done any calculations on this front, give it some rigidity. Right, if I have some highly symmetric cap with a huge number of internal dimensions, I feel like if I ping that cap, at least if I ping that cap with some low dimensional perturbation, the huge number of internal dimensions are going to make it somehow rigid against that perturbation. And I suspect that when you're trying to study the equations for shape deformations of sufficiently symmetric extremal surfaces, they'll simplify as a result in a large D limit. This is related to many interesting physical questions. It is related to the problem of finding Einstein's equations from the boundary theory, which I know many of you at UBC are very familiar with. I know Mark was one of the pioneers of this field. There's a problem of trying to reproduce the bulk Einstein's equations non-perturbatively from entropy considerations on the boundary. This was done originally using, perturbatively using the equivalence between bulk and boundary relative entropy and the first law of entanglement entropy. Given the conjectured relationship between bulk and boundary modular flow, there are some directions towards doing this non-perturbatively using modular flow considerations. But all of them sort of, in some sense, have at their core the problem of doing shape deformations of extremal surfaces. And I think that that is an interesting way to try to go about reconstructing Einstein's equations. And similarly, possibly you could also think about the holographic metric from similar considerations, although I don't really have anything more to say about that. Another thing that shape deformations have been related to are the quantum null energy condition. There was a paper a few years ago when the quantum null energy condition first appeared, which proved the quantum null energy condition for holographic CFTs using shape deformations of Ryutaki-Nagi surfaces in the bulk. Now, the quantum null energy condition has now been proved for general quantum field theories by Tom Faulkner and collaborators, but it's still very clear that, you know, at least in holographic theories, the quantum null energy condition is closely related to these shape deformations. So maybe you could find some interesting questions about energy conditions or focusing in holographic field theories that simplify in large D as a result of this potential simplification of shape deformations. Another thing I want to say is just general modular flow. Both the reconstruction of Einstein's equations and the QNEC are intimately related to the problem of bulk and boundary modular flow. I don't have anything specific to say about this, but I do think it's possible that there are interesting modular flow questions that one could answer in large D. For example, there are some interesting calculations involving trying to compute the modular Hamiltonian. So, you know, the modular Hamiltonian of a half space is very well understood. If you do small deformations to that half space, you can solve for the modular Hamiltonian perturbatively. In a holographic context, this is related to the problem of shape deformations. Perhaps you could do something like that holographically and understand, get a better understanding of modular flow for perturbations around simple regions. This would be very interesting because modular flow is very, very closely related to entanglement wedge reconstruction. If you have not heard a lot about modular flow, but this sounded interesting to you, there is a recent paper, I'm afraid I don't remember who the other author is. It's Ankar Parakar and one other author. If anyone knows who it is, please put it in the chat, where they compute modular Hamiltonians for excited states in generic field theories using path integral techniques. But this paper has a very, very nice review of recent developments in modular flow, especially as it relates to holography. So that would be, I think, my recommendation for a place to look if you are interested in learning more about that area of research. Okay, that's all I wanted to say about shape deformations. Another interesting problem would be the large Dcf T calculation. Now, I should say what I mean by the CFT calculation, because it's not clear at all that CFTs exist in arbitrarily large dimensions, but you can still set up the mutual information calculation on the boundary, thinking of the mutual information as a correlator of twist operators. So in D equals 2, which is 3 bulk dimensions, this was very famously done analytically by Tom Hartman in 2013. In D greater than 2 dimensions, however, it is, as far as I know, not been done in any case. We do believe that it is possible that it may be, that this calculation may become tractable in the D goes to infinity limit. There are problems related to the fact that, you know, a twist operator in 2 boundary dimensions is just an operator at a single point, whereas as you go to larger and larger dimensions, twist operators are smeared over submanifolds of larger and larger dimension, which does make the calculation difficult. But I mean, someone who is really good at CFT and who's interested in this kind of calculation should certainly think about trying to do this. I'll pause for a moment because, Sean, are you still here? Would you be interested in saying a few more words about this calculation, because you were the one who spent the most time on it?
Yeah, I can say a couple of things. So as John said, you have to compute the entanglement entropy of A and B, you have to compute a 2-point function of these surface operators where the surface is the boundary of the region, and that 2-point function is hard to compute in general. And there's some literature on computing these 2-point functions of surface operators, but not enough has been done for us to actually figure out how to compute this entanglement entropy.
Yeah. Here's what Sean's saying. We have regions A and B and twist operators that are smeared over the entire boundary. We need to compute their correlator. There is some work that Sean looked at which involves a large D simplification of conformal blocks by Jared Kaplan and some collaborators, which would be a good place to look if you're interested in trying to solve this problem. And certainly, you know, let us know if you make any progress, because it's a good problem that someone should solve. Okay, so the other thing I want to say, which this one is perhaps very ambitious because I have no idea if this will work or not. I haven't thought, I thought about this for the first time a couple of weeks ago and I haven't dedicated any real time to it. So let me just say it very speculatively. Saddle points in the path integral, in the gravitational path integral. The gravitational path integral, I think, has been interesting forever, since the 70s at least, since Hawking made a lot of advances in the gravitational path integral. But I think especially in recent years, we've seen saddle point analysis of the gravitational path integral become very, very powerful for trying to compute information-theoretic quantities. One, for example, is the computation of Rényi entropies for holographic states without U1 symmetry. The case where the path integral that prepares a state has a U1 symmetry, the gravitational path integral in that case for the Rényi entropy can be solved exactly. This has been known for quite some time. But the absence of a U1 symmetry, which is a generic state, if you're trying to compute the Rényi entropies of a generic state, you need to set up some quite complicated gravitational path integral. And as far as I know, the only analytic answer for computing Rényi entropies exactly using a saddle point analysis of the gravitational path integral is in D=1. And that's the replica wormholes West paper in a JT example. There are, many really amazing partial analyses, non-complete analytic answers in more complicated models. A quick survey of those. There are the replica wormholes East paper in D=1 in a very interesting example. There's a truncated analysis for 2 intervals in D=2, which is due to Tom Faulkner. There are these general arguments due to Lukowitz and Maldacena. But I believe that actually computing Rényi entropies exactly using, fully analytically using a saddle point analysis of the gravitational path integral is a very interesting problem. And the fact that it is possible in D=1, partially possible in D=2, and seemingly impossible in higher dimensions indicates to me that possibly we should start looking at D=∞. Now, there are pros and cons to this idea. The pro is that the large D limit, I believe, will suppress many saddles in the gravitational path integral. The reason for that is that the gravitational action of the spacetime that shows up in the gravitational path integral is weighted by volume, right? The gravitational path integral, or the action, is an integral of the scalar curvature, which certainly scales in at least some sense with the volume of the spacetime. And I imagine that as we have larger and larger internal dimensions for our saddles, we're going to see a lot of perhaps symmetry breaking saddles being heavily suppressed as a result of that large D limit, as a result of the large number of internal dimensions. The con of trying to look for saddle points in the gravitational path integral in large dimensions is that the Riemann tensor has many independent components. Now, in D=2, there's only one independent component of the Riemann tensor. So the Riemann tensor is determined entirely by the scalar curvature. This is why, for example, saddles in D=2 gravity, or sorry, this is D=1, which is 2 bulk dimensions. Saddles in GT gravity are very simple for this reason. They are saddles of constant curvature, and the reason that's consistent is because the Riemann tensor has only one component. So every spacetime is determined entirely, sort of the local structure of a spacetime is determined entirely by its scalar curvature. In D equals 2, there are 6 components, and the Riemann tensor is determined entirely by the Ricci tensor. So again, in D equals 2, this can be used to show that the full local structure of a saddle of Einstein's equations is determined entirely by the Ricci tensor, which is itself very constrained by the equations of motion. But as you go to D goes to infinity, the size of the Riemann tensor gets much, much bigger than the size of the Ricci tensor. And that, so for example, the number of components of the Riemann tensor scales as d to the 4th, whereas the number of components in the Ricci tensor scales as d squared. So that is going to be a problem in trying to do any of these analyses. You can no longer make these very simple arguments where you say, well, every saddle has some universal local structure, right? Use this in D equals 2 to say every saddle has constant curvature, constant scalar curvature. Use this in D equals 3 to say every saddle has to be a locally hyperbolic manifold. That's something that you won't be able to do in large D, but nevertheless, I remain optimistic that one might be able to do something. There are, of course, Renyi entropies are the things that are most interesting to me because it's my bias. But of course, there's plenty of interesting work in computing partition functions using saddle point analysis of the path integral. Renyi entropy is really just a special partition function. It's a partition function on this weird replica manifold, but for a general partition function, you know, people are generally interested in, for example, partition functions on the torus. We know how to do 2D partition functions. So that's, sorry, D equals 1. We know how to do partition functions in JT gravity, thanks to, for example, the work of Saad, Shenker, and Stanford. We know how to do torus partition functions in D equals 2, thanks to many people, but for example, perhaps most famously, Maloney and Witten. But as far as I know, we don't know how to do any dimensions above that, and perhaps we might imagine that some sort of infinite dimensional torus maybe, or you know, large dimensional torus may be an object on which it is possible to do some saddle point analysis of the partition function. I don't have any actual concrete ideas for how one might do this, but if you could do it, I think it would be very, very interesting. So I think I'll stop there. That's everything I want to say. Thank you very much for your attention, and I'll happily take questions.
All right, thanks, John. For everyone. Is there any questions?
So it's, well, comment / question. Something that acts the same as dimensionality, like in the sense, well, in many senses, but for example, the sense of when you wrote the blackening factor and had the power d-2 on the R over RH piece is, well, what's sometimes called a hyperscaling violation exponent. And so something you can do to get the same sort of physics is to take that parameter large. That's like a sharp parameter in field theory that you could tune.
Can you tell me more about this parameter? I don't know what it is.
Well, well, theories that violate hyperscaling are sort of very closely related to conformal theories. I mean, in the holographic context, probably the relevant example is to think of a stack of DP branes, but P not equal to 3. So then you have these non-conformal theories that live on the world volume, and they have some bulk dual.
Okay.
There's some RG flow, and in that context, those theories are very closely related to theories that violate hyperscaling.
Okay.
And an example that's very closely related to this D goes to infinity limit is the class of NS5 branes, where it's effectively like a D goes to infinity limit. Again, in the sense of the scaling of emblackening factors, or how the entropy scales with energy. And I'm curious if the theory you're considering is non-local, so it's kind of hard to think about these, at least for me, these quantum information type quantities. But there I wonder if the types of things you're saying have actually some kind of sharp application to that particular theory, which I think is still pretty mysterious.
Yeah, I think that's a very interesting question. I mean, you've landed on something which is sort of interesting, which is that this large D, or in your case, this other large parameter, always buys us something and always kills something else. You know, when you're trying to do the CFT calculation, it buys us these simple conformal blocks, but it kills the locality of the twist operators. What you're talking about, it sounds like it buys us, you know, some other scaling, but possibly kills the locality of the theory. Yeah, I don't know. I mean, it sounds interesting. I don't have any comments about it because I don't know the theory that you're talking about, but it sounds plausible.
Yeah, I mean, if you don't take the dimensionality large, you sort of have to kill the locality of the theory because, you know, the formula you wrote, there's some scaling of the entropy with energy of those black holes. And as you take d to infinity, it becomes linear in the energy. And if you keep the dimension fixed and land on that same answer, that's a Hagedorn scaling. So that's why it's related to non-locality. And the concrete theory that I said, it's some sort of little string theory that people study. But yeah, indeed, it complicates it in that way.
Okay, interesting.
Actually, can I ask a question about the question?
Go ahead. Yeah, please. I'm happy to have some discussion.
Yeah, I'm just wondering. There's another similarity. Roberto is here, so you know there is this Witten black hole that emerges at the large D limit. So it's another similarity to the NS5 brane. I'm just wondering if this analogy could be made more precise in some sense, or is it just an analogy?
So what exactly do you want to make more precise?
The analogy you make between the large D limit and this taking this hyperscaling parameter, is it more than an analogy, or is there any sort of precise mapping between these two limits? Because now that you mention it, there's a lot of similarities there.
Yeah, well, there's no precise mapping in the sense that, of course, the theories are different. They're different number of dimensions. One's conformal, one's not. But at the level of the thermodynamics, they're pretty equivalent. Like the entropy scaling for these theories generally is temperature to the d minus theta. Theta is the hyperscaling violation, critical exponent. So of course you can take d large, you can take theta small. And it can become negative. There's no issue with that. So that's these condensed matter people speak of an effective dimensionality, which is given by d minus theta. So in a sense, that's the relevant thing to try to tune. And people several years ago wrote papers about these theories in a kind of bottom up, holographic condensed matter sort of point of view. But in the DP branes for p not equal to 3, those are sharp examples where they're very much like this. Especially for the NS5 brane is the interesting limit of theta going to minus infinity, because you get the Hagedorn scaling and it.
Right. That's interesting.
Yeah, I always wondered how to use these large D ideas in that context, because I feel like something sharp should be able to be said, but I never knew what it was.
Yeah, no, that would be. I'm one of those people who worked on that many years ago, so I'm. Interested. Yeah, that's interesting.
Thank you for the discussion. I don't know if anything more to say about it, but I am happy to take other questions.
Yeah, maybe I can say something or ask something that may be a little speculative. You mentioned this. You've been talking about this decoupling, which is. I don't know whether the word decoupling is the most appropriate one. Maybe you want to talk about the dilution of the entanglement gets diluted, right? And that's the same effect that usually when you study statistical mechanics, that's, that one way of taking the mean field theory limit is by taking large D limit. And that's related to what you mentioned, that dynamical mean field theory is a large D limit. Now, in these cases, the large limit, when it becomes very useful is when you get some sort of effective theory that allows you to compute things in a more efficient way. Now, do you think that there could be some effective theory that allows to compute information-theoretic quantities at large D? As something that, there's something that Mark Messey has been doing on
with
some
his
sort of
entanglement hydrodynamics, right?
Exactly. And there's connections between the fluid gravity and large D. They are very similar. So I don't know whether there might be something like that some effective theory at large D that allows to compute some information-theoretic quantities.
Yeah,
I mean, I have nothing precise to say, but
right. I think the best thing we have right now in that direction is, like you mentioned, Mark Mazai's entanglement hydrodynamics, and collaborators. I don't want to give the credit just to one person. I mean, so because the best tool we have for understanding entanglement holographically is the Ryutaki-Nagi formula and its covariant and quantum generalizations, it seems hard to imagine for me that you will get something that doesn't come directly from geometric considerations. And that's the kind of thing that Mark is building. So perhaps one should look at Mark's techniques and, you know, see if there's something that can be said at large D about this kind of emergent effective description. I think it's hard to imagine that you would be able to get, you know, some effective entanglement description on the boundary alone without appealing to the RT formula, just because the whole magic of the RT formula is that it makes those kinds of calculations much simpler. Yeah. But I think that perhaps looking at the kind of thing that, well, you know, this thing I said about the shape deformations, it's entirely possible that looking at shape deformations, I mean, Mark is very concerned with, you know, long time evolution of extremal surfaces, right? What happens to them as you go through some sort of quench or some sort of evolution, long time evolution in the black hole background.
Yeah.
I would suspect that if we look at something more local, if we look at, for example, these shape deformations of extremal surfaces, that could be the kind of thing that might develop some effective theory in the large D limit. And then we might get some interesting description.
Yeah.
I will say that quantum information theorists already call, there's already a term, entanglement dilution, so I'm afraid we can't use that.
Okay. Okay, good. Thank you.
I also considered entanglement localization, but apparently that's been used a few times by some niche authors. I shouldn't say that, maybe some of you are here. I just don't know the papers very well.
And have you considered quantum error correction? Error correction at large D?
I have not. I have nothing to say about it. I thought about it before this talk because I was thinking about trying to put something about quantum error correction in, but off the top of my head, I cannot think of any way for that to simplify at large D, if only because, well, our best examples of, our understanding of quantum error correction in ADS-CFT largely is pretty heuristic. It largely has to do with, you know, acknowledging that RT surfaces overlap in certain ways. You know, this is the main insight of Almiri Dong Harlow, is this, you know, complementary recovery and this robustness to erasure errors. All of that is fairly heuristic and in that sense pretty dimension independent. So I don't see what you would be bought in large D. The most concrete stuff we do have towards understanding holographic quantum error correction comes from tensor networks, which really only makes sense to me in D = 2. If you were to try to build some large D tensor network, perhaps you could say something interesting about quantum error correction in that regime, but I'm not even sure what you would be looking for. Like, I don't know what kind of thing you would want to find there that you can't find in low dimensions. So I decided not to put it here because I'm not sure what the concrete question is.
Thanks.
All right. If there's no further questions, thanks, John, for a great seminar. I'm glad there was lots of interactivity. And
Yeah,
we'll let
thank you all
go.
so much. Okay. Have a nice day, everyone. I'll see you eventually, I'm sure.